In this video, I'm going to cover chapter 2 of my stochastic modeling book. That's the chapter about the distribution and the conditional expectation of a random variable. So like in the previous video, you can see that all the topics we are going to cover are represented in the form of a directed graph that also shows the connections among the different topics. In case you are interested in one specific topic, check out the thumbnail of this video or the description of the video with the list of the topics we are going to cover and exactly when we are going to cover them. So this video is in fact divided into 3 parts. You see the concept of distribution of a random variable is covered here, and the concept of conditional expectation of a random variable is covered here. But you see that those two concepts are related to this notion of Radon-Nikodym derivative. Okay, so the Radon-Nikodym derivative is something that comes from a very general result in measure theory called the Radon-Nikodym theorem. So that's the first thing we are going to do. I'm going to explain this theorem. So the proof is very long, so I'm going to skip the proof. The goal of this video is not to cover measure theory, it's instead to use this theorem and to see its implications in the context of probability theory. So I'm only going to state the theorem without the proof. And I'm also going to insist on the reason why the theorem makes complete sense, in fact. Okay, that's a result that we expect, even if the proof is kind of difficult. The theorem says more or less that if you have two positive measures and one measure is absolutely continuous with respect to the other one, so we have the notion of absolute continuity here, then those two measures are related by some positive measurable function that we call the Radon-Nikodym derivative. Okay, so that's again an important concept in measure theory with important implications in probability theory, and in particular in the notion of distribution or in the notion of conditional expectation. So that's going to be the first part. Then we are going to define the notion of distribution of a random variable. So the distribution of a random variable is a measure, but contrary to the very abstract probability measure P defined on the sample space omega, this measure is just a measure defined on the Borel set. So that's a more friendly measure that we understand better. And after defining this, I'm going to prove an important theorem called the change of variables formula that basically tells you that to compute probabilities of events involving a random variable x or expected value of functions involving your random variable x, instead of integrating some function with respect to the probability measure, you can instead look at the integral on the real line of the distribution function. Okay, so that's what we call the change of variable formula. That's an important formula that we use in probability that is useful to actually compute probabilities or expected value. All right, so then after that we'll see the connection between this notion of distribution and the notion of Radon-Nikodym derivative. So what we are going to see is that typically the distribution is related to the Lebesgue measure or something that we call a counting measure. In the continuous case, in the case of continuous random variable, the distribution is absolutely continuous with respect to the Lebesgue measure. And the corresponding Radon-Nikodym derivative is in fact the density function. Okay, the density function of this random variable. If at the opposite your random variable is discrete, then the distribution is going to be absolutely continuous with respect to something that we call a counting measure. And the corresponding Radon-Nikodym derivative, okay, of this distribution with respect to the counting measure is nothing else than what we call the probability mass function of the random variable. Okay, so we will see basically that this concept of Radon-Nikodym derivative in some sense unifies the theory of continuous random variable and discrete random variable from this point of view of like more general measure theory. In fact, the continuous case and the discrete case are in fact the same, okay? just with respect to different reference measures. Okay, so that's going to be the second part of the video after we cover the Radon-Nikodym theorem. Then third, we are going to look at the concept of conditional expectation. So if you took a class in probability theory at the undergrad level, you probably saw this notion of conditional expectation or conditional probability. So conditional expectation of a random variable or conditional probability of an event, but given another event. Here, what I mean by conditional expectation is a much more abstract concept. That's the concept of conditional expectation of a random variable with respect to a sigma algebra. Okay? So, there is a definition, like an abstract definition of the notion of conditional expectation that I'm going to give you, but there is also some intuition behind that basically tells you what the conditional expectation should be. Now, it turns out that our intuition of what the conditional expectation should be and this abstract definition is not clear. The connection is not clear. So I came up with some kind of visualization that I'm going to show you to basically show you that indeed the abstract definition of conditional expectation makes sense. That's indeed what we want to be able to model our intuition of what the conditional expectation should be. So that's going to be step one. I'm going to define the concept and I'm going to spend a lot of time commenting on the definition and why this definition makes sense. Then, again, like for distribution, we are going to look at the connection between the Radon-Nikodym derivative and the conditional expectation. So in this context, the Radon-Nikodym derivative is a key. Basically, from the definition of conditional expectation, it's not clear that this notion, this object exists or is unique. We are going to use the Radon-Nikodym theorem to prove that the conditional expectation indeed exists and is unique. Okay? Then after, I'm going to look at applications of this general concept. So we'll have two parts. First, I'm going to look at this part here, where we look at something that I want to call conditioning techniques. So what we'll do is use the conditional expectation or conditional probability as a tool to be able to compute unconditional objects, so unconditional expectation or unconditional probabilities. So you remember that in the previous video, I mentioned that there are three main tools to compute probabilities. One, combinatorics, if you are in a symmetric probability space and you deal with simple events. If your events are a little bit too complicated, you can use a Venn diagram to simplify some expression, and eventually you can come back to the first tool, which is combinatorics. And I mentioned that there is a third tool to compute expected values in general or probabilities. It's conditioning. So that's what we are going to see here. To compute the expected value of a random variable or the probability of an event, you can condition on a sigma algebra. This sigma algebra can take the form of a partition, if it's a sigma algebra generated by a partition, or another random variable. Okay, so I'm going to prove a couple of formulas here. These are typically formulas that we see at the undergrad level, but at the undergrad level, those formulas are extremely difficult to prove because they involve a lot of messy algebra. But using the approach of measure theory, these formulas are almost straightforward. Okay, so we are going to basically see that important formulas at the undergrad level can be recovered from this very general concept of conditional expectation. So that's going to connect this theoretical approach and things that are more basic at the undergrad level, except that now we are going to have a direct proof of all that. Okay? Then finally, I'm going to tell you about properties of the actual conditional expectation. In this part, we are going to use the conditional expectation as a tool to compute unconditional objects, unconditional analog. At the opposite, in this part, we are actually going to look at properties of the conditional expectation. And so in particular, I'm going to tell you about something called the projection rule, or look at the conditional expectation of a random variable given a sigma algebra when this random variable is measurable with respect to the sigma algebra or independent of the sigma algebra. That's two extreme cases, one called perfect information, the other one called independence. Those properties are going to be very important in future videos to study Markov chains and martingales. In particular, that's by using those properties that if you have a process, you can actually prove that the process is a martingale or a Markov chain. So first, let's look at the Radon-Nikodym theorem. And before I state the theorem, I'm going to give you some motivation behind the theorem. So imagine that in the background, we have a measurable space omega f. Omega is a set, f is the sigma algebra. That's defined in the previous video. Then on this measurable space, I'm going to define mu, a positive measure. Okay, so mu is defined on the sigma algebra. You can look at mu of measurable sets. And I'm going to consider also a positive measurable function phi. So phi is defined on omega f with value in the real line with the Borel sigma algebra. We assume that this function phi is positive. That's important. Okay? And then I'm going to, from those two objects, define a new function, nu, on the sigma algebra f, like this. So for all measurable set A in F, I'm going to call nu of A the integral on the set A of phi d mu. So by integral on the set A, what I mean by that is basically the integral on all omega of the function phi, but times the indicator function on A, so that means that we only look at the function phi on the set A. Okay, we saw in the previous video that the integral of a positive measurable function with respect to a measure is well defined. I gave the definition, it's always well defined. It might be infinite, but it's well defined. All right, so by defining nu like that, what we do in fact is we define a new positive measure. Okay? You see that clearly if phi is constant equal to 1 on omega, then nu is equal to mu. And so you can view phi as some kind of function that's going to deform the measure mu, and we are going to still end up with a measure that now we call nu. Okay, so how can we prove that indeed nu is a positive measure? If you go back to the previous video, you will see that a positive measure is just something that is sigma additive, so we only need to prove that nu is sigma additive. For that, we basically take a sequence of measurable sets An in the sigma algebra F. We assume that those sets are mutually exclusive, and we want to prove that nu of the union of the An is equal to the infinite sum of nu of An. And the proof is just here, it's a consequence of the monotone convergence theorem, okay? That basically says that nu of the union is equal to the infinite sum of nu of An. So, how do we prove that? Well, first step, you just look at the definition of nu and realize that nu of the union here is just the integral of phi times indicator function on of the union of the An d mu. But because those An are mutually exclusive, the indicator function on the union is just the sum of the indicator functions. Okay? That's what I'm using in this first step here. I'm just rewriting this as the integral of the infinite sum of phi indicator function of An d mu. Then, for the next step, I'm going to use the monotone convergence theorem to extract the infinite sum here. You see, we have the integral of the infinite sum, and then suddenly that becomes the infinite sum of the integrals. That's a consequence of the monotone convergence theorem, but that's a little bit hidden. So, remember from the previous video that the conclusion of the monotone convergence theorem is that the integral of the limit is equal to the limit of the integrals. This is true if you deal with a sequence of, a non-decreasing sequence of measurable functions. Now, it turns out that you can view this infinite sum as the limit of a monotone sequence. So how do we do this? Well, by definition, the infinite sum is the limit of the partial sums, okay? But the partial sums of those functions is a non-decreasing sequence because we assume that phi is positive, and clearly this indicator function also is positive. So at each step, we just add something positive. So the sequence of partial sums is in fact a non-decreasing sequence of measurable functions. Okay? And so thinking of the infinite sum as the limit of the partial sum, you can put the limit outside by the monotone convergence theorem, by monotonicity of the sequence of partial sums, but then you end up in the integral with a partial sum, so that means a finite sum. But then the integral of a finite sum is the finite sum of the integrals, just because the integral is linear, okay? And so eventually you have that this part here is just equal to the limit of the partial sums of the integral. But again, I'm using the fact that the limit of the partial sum by definition is the infinite sum. So we are using several things here. Step one, we use the fact that infinite sum is equal to the limit of the partial sums. Step two, we use the fact that because the sequence of partial sums is monotone, we can use the monotone convergence theorem and put the limit outside the integral. Step three, we use the fact that the integral is linear to put the finite sum outside the integral. And step four, exactly like for step one, we use the fact that the limit of the partial sum is the infinite sum. All right, so that's everything we use here. We use a bunch of stuff in this to get this equation. Then, when you end up with that, you see that this integral is just, by definition, the same, it's of the same form as this, but with an instead of a. And so this integral here is just nu of an. And then you end up with infinite sum of nu of an. So that shows that indeed nu is sigma additive, so that's a positive measure on f. Okay, so that was just a warming up. The Roydon-Nikodym theorem is much more difficult than that. It's basically it looks at the same problem here, but instead of having mu and phi given, in which case you can easily construct this new object, now mu and nu are given, and you want to find phi that satisfies this. Okay, so phi becomes your unknown, and you want to try to construct a function phi that satisfies that. Okay, that's the main question behind the Roydon-Nikodym theorem. Given two measures, mu and nu, can we find a positive measurable function phi such that, well, this equation here is satisfied? Is it true or not? Okay, so like I told you, I'm not going to prove the theorem because the proof is extremely long and it's quite difficult, but we can kind of guess the answer. Not exactly the form of the function phi, but say that, like, see all the cases where indeed there must be a such function phi or not. Okay, and so for that I'm going to use a basic analogy with like very simple calculus. Let's imagine that you have the very simple equation here, ax equals b, that you want to solve. Okay, so a and b are just real numbers, and you want to find x such that ax equals b. Think of a as your measure mu, and b as your measure nu. A and b are given, like here, mu and nu are given, and you want to find x. Well, we know from basic calculus that this equation has a unique solution, okay, if and only if a is different from 0. Okay? And in this case, the solution is just given by b over a. Okay, so if a is equal to 0, then doesn't matter how you choose x, x is always 0. So you have no solution if b is different from 0, Or at the opposite, you have infinitely many solutions if B is equal to 0. So the condition for existence and uniqueness of a solution in this case is the fact that A must be different from 0. Okay, so there is some kind of analogy with that. So what does it mean in the context of the Radon-Nikodym theorem that A is equal to 0 in some sense? So if you go back to the problem here, you see clearly that if there exists A in F, a measurable set A, such that mu of A is equal to 0, that's going to be the analog of A equals 0, but nu of A is strictly positive. Remember that now mu and nu are given. So if there exists a set A such that mu of A equals 0 and mu of A is strictly positive, then we cannot find any such function phi. Okay, that's obvious because if there is such a set, then because nu of A is equal to 0, this integral here, that's an integral on a set with measure 0 for the measure mu. So that integral is 0 and that cannot be strictly positive. So there is no solution in this case. And so what we can at least say is that we do not have any solution if there exists a measurable set A in F such that mu of A is equal to 0, but nu of A is strictly positive. It's obvious that in this case we do not have a solution. Now, what the Radon-Nikodym theorem says is that in any other case, we have a unique solution, analog to that, okay? In any other cases, meaning that if A is different from 0, then we have indeed a unique solution to this problem. So, for that, I need to introduce some assumption on the theorem that's going to basically exclude this case. We do not want any measurable set A such that mu of A is 0 and mu of A is strictly positive. And so that brings us to the notion of absolute continuity. We say that nu is absolutely continuous with respect to mu. That's the meaning of this symbol here that I'm using. If this is not possible, that means basically that for all measurable set A in F, mu of A equals 0 implies that nu of A is equal to 0 also. So that excludes those cases. Then, again, by analogy with this simple example, we kind of guess that if nu is absolutely continuous with respect to mu, then there must be such a function phi. Okay? So, again, the proof is extremely difficult, but intuitively we expect that, and what the theorem says is that indeed that's correct. So the theorem says that if nu is absolutely continuous with respect to mu, and we need to add one extra assumption, we need to assume that omega f mu is sigma finite. I remind you from the previous video, sigma finite means that the set omega can be written as a countable union of measurable sets with finite measure for the measure mu. That's the definition of sigma finite. So if we have those assumptions, then there is indeed a unique solution to this problem. We can find a unique positive measurable function phi such that nu of A is equal to the integral on A of phi d mu for all A in F. Okay, so here, by uniqueness, we mean unique mu almost everywhere. So what does it mean, mu almost everywhere? That means that if phi1 and phi2 are two positive measurable functions that are solution to this problem, then the set of omega in capital omega such that phi1 of omega is different from phi2 of omega is going to be a set with measure 0 for the measure mu. Okay? So that means that the different solutions are going to be equal everywhere except on maybe a set, but this set has measure 0. Okay, that's what we mean by mu almost everywhere. So that's the conclusion of Radon-Nikodym theorem, again analog to that. if nu is absolutely continuous with respect to mu and you have sigma finiteness, then there is a unique solution to this point. Okay, so a little bit of history. The theorem was proved first by Roidon in the case where omega is equal to Rn, and then a few years later, Otto Nicolin was able to extend the theorem to very general measure spaces, not limited to just Rn. Okay, and then to conclude, just one definition. This function phi that is positive measurable and unique solution to this problem is called the Roidon-Nicolin derivative of nu with respect to mu. And that's written that way, phi is equal to d nu over d mu. So that's this concept of Roidon-Nicolin derivative that is going to be important now to define, to study the notion of distribution and then the notion of conditional expectation of a random variable. So now let's look at the concept of distribution of a random variable. So in this context, I'm going to have a probability space in the background, omega fp. Okay, omega is the set of all the possible outcomes. F is the sigma algebra on omega, so that's the set of events. We defined all that in the previous video, and P is your probability measure defined on the set of events. So what we call the distribution of X, or also called the induced measure, the measure induced by X, is this measure now defined on the Borel sigma algebra, defined by, for all Borel set B, nu X of B is the probability that X is in B. So first, let's see that this is indeed well defined. Remember that X random variable means exactly that X is measurable. And so that means that the preimage of any Borel set by the function X should be measurable. In the set, in the measurable space omega f, so that means that this set here is indeed an event, is indeed in the set of event f. Remember that I use X belongs to B as a short to say the set of omega in capital Omega such that X of omega is in B. That's the same as the preimage of B, the Borel set B, by the function X. So this is indeed an event, and so the probability of that is indeed well defined. Okay, so that's how we define the distribution. Remember also that the measure of a set can also be defined as the integral on omega of indicator function on this set d mu, if mu is your measure, now it's p, so dp, that gives you that, okay? That's the integral with respect to the probability measure p, but now this set is exactly the preimage of b by the function x, okay? So you have this definition. So notice that thanks to this definition, we go from a probability measure that we don't really understand, defined on f, the set of events that are themselves subsets of omega. But this omega fp is difficult to understand. Now what we do with this transformation is that instead of looking at probabilities of events, we look at the measure of some Borel sets that we understand better. Okay? So instead of having a probability measure p defined on f, you have now a measure called the distribution of x defined on the Borel sigma algebra. Okay? If you took undergrad level probability, you probably heard about the notion of distribution function. Okay? The distribution function is a more particular object. That's not a measure, that's just a function. This is a more abstract object, that's a measure. The connection between the two is that the distribution function that we typically call capital F at some point little x is defined as the probability that x is less or equal to this little x. That's a particular case of that when you assume that the set B is equal to the interval negative infinity x, okay? Close at x, the notion of distribution is much more general. It's but you can look at it as some kind of extension of the notion of distribution function. All right, so let's look in picture at what happens here. You have basically three sets that are involved. The real line with the Borel sigma algebra, omega f, that is a much more abstract space, the sample space with the set of events, and the interval 0, 1, which is the possible values of your probability. And then you have functions that are defined here. You have the random variable x, that is a measurable function defined on omega with value in R. So the function x goes from here to here. Then, of course, x minus 1 is going from R to omega, okay? And you also have your probability p. The probability p is a measure, okay? So that's not defined again on omega, that's defined on f, okay? And the transformation we do here is that instead of looking at events in f and looking at probability of those events, instead we look at Borel sets here, and we look at x minus 1 of these Borel sets, which brings us in the sigma algebra here, and we look at the probability of that event, which is here. Okay? So instead of having a measure p that is theoretical defined on a very general measurable space omega f, now we have a nicer measure, a more friendly measure that is defined on the Borel sigma algebra. Okay? So, how is it useful in practice? Well, it turns out that instead, thanks to this distribution, we have this theorem called the change of variables formula that tells you that instead of integrating with respect to the probability measure p, you just have to integrate with respect to this new distribution. This distribution still looks abstract, but we will see soon that when we deal with continuous or discrete random variables, there is a way to rewrite this distribution using probability mass functions or density functions. Okay, but for now, what we are going to prove is that expected value of h of x, which by definition, so h is going to be a positive measurable function or an integrable function defined on the real line with value in the real line. So h of x, okay, is going to be a function defined on omega with value in R, okay? So, and it's still measurable, like the composition of measurable functions is again measurable. That's a basic consequence of the definition of measurability. So h of x is again a measurable function defined on omega. So h of x is again a random variable. Okay? So why do we look at this very general thing? It's because expected value of h of x can be used to generate whatever you want that is useful in probability theory, depending on the choice of h. So for instance, if you take h equals identity, you get expected value of x, but in the same way you can compute expected value of x squared, the different moments of x, or you can take h to be of the form of an indicator function like here, and then this becomes a probability. Okay? So probabilities of events involving x of or expected values of functions of x can all be written that way. So, because h of x is a random variable, okay, you can just compute this expected value by definition as the integral on omega of h of capital X dp. That's the thing we don't want to do, okay? Integrating with respect to a probability measure, it's not clear. It's not clear how we should do that. And what the change of variables formula tells you is the fact that, well, this thing is in fact the same as the integral, but on R, that we know better, of h, but now with respect to this distribution, okay, with respect to this new measure, okay? So, again, it turns out that this is true for all positive measurable function and all integrable function h defined on R with value in R. Okay, so the proof is interesting because the proof follows basically the 4 steps of the construction of the integral that we saw in the previous video. And it's interesting also because that's a typical technique in measure theory and probability theory. For many theorems, the way you prove those theorems is by first proving the result for indicator function, then you use linearity of the integral to deduce the result for simple functions that are linear combination of indicator functions. And then after you use the monotone convergence theorem to go from simple function to positive measurable function using the fact that any positive measurable function can be written as the limit of a monotone sequence of simple function. That's something we saw in the previous video. And then after you can use again linearity to go from positive measurable function to integrable function using the fact that any measurable function can be written at its positive part minus its negative part. And both the positive part and the negative part are positive measurable. So that's a typical technique in measure theory or probability. You just need to prove the result for indicator function. And then you just follow the steps of the construction of the integral using the monotone convergence theorem to go from simple function to positive measurable function. So more concretely, the proof looks like that. We more or less need to focus on the case where h is an indicator function. Here, by going from indicator function, simple function, positive measurable function, integrable function, I'm talking about the function x, h. X is fixed. H, we want to prove the result for all h like that, so that's the step we follow. So, step 1, we need to prove the result when h is an indicator function. That's easy, that almost follows from the definition. And then the rest of the proof follows from the construction of the integral. So more precisely, we have this for, the proof follows the construction of the integral. So let's assume that h is equal to the indicator function on a Borel set B. Then in this case, the expected value of h of b is exactly the same as the expected value of indicator function on the set B of x. What we mean by that, it's basically the function defined on omega, okay? And this function at point omega is basically equal to 1 if x of omega is in the set B. So we can rewrite this indicator function on B of x as indicator function on the set where x belongs to B. That's exactly this set here, that's exactly this event, okay? That's just a matter of notation, okay? So we have this. Remember that the expected value of a random variable is the integral of this random variable dp. In this case, the function inside the expected value is an indicator function, so that's going to be just integral on omega of this function dp, but the integral of an indicator function with respect to a measure, that's just the measure of the measurable set in the indicator function. So this is just the probability that x is in B, okay? That we get here. But by definition, this is exactly nu x of B, okay? And again, by definition of integral of an indicator function with respect to a measure, this integral here is just the distribution, the value of the distribution on the set B, so that's exactly this value, okay? So we get that, and so that shows that indeed this expected value here is equal to this integral that we recognize here, but h is the particular case indicator function on the set B. Okay, so that's step 1, that proves the result when h is an indicator function. So how do we extend the result to simple functions? Remember that a simple function is going to be a function that is measurable with a finite range that can only take a finite number of values, and so such a function can be written as a linear combination of indicator functions. And the only thing we need to use is the fact that the integral, or in this case, integral with respect to p, so that's the expected value, is linear. And so the expected value of the linear combination is the linear combination of the expected value. Okay? The proof is just like that. Let's assume that h is a simple function. Then h can be written as a sum for I going from 1 to n of little ai times indicator function on capital AI of x. Of little x, in fact, for just the function x. Those little ai are just real numbers. The capital AI must be, like the set B, must be in your Borel sigma algebra. Alright, so if h has this form, then expected value of h of x is just that. Okay? Then you use the fact that the expected value is linear, and so you can extract the finite sum of the AI, this linear combination, and you end up with that. You just extract the sum from the expected value. And then here, you recognize that we have something of the same form as here. So using step 1, you know that this quantity here is equal to the integral of the integer function ai d nu x from the previous step. And then, now you again use linearity of the integral, but now instead of using linearity of the expected value, which is integral with respect to p, you use linearity of the integral with respect to nu x. And you just said that the linear combination of the integral with respect to nu x is equal to the integral of the linear combination. But the linear combination is just equal to h again, that was here. And so you end up with exactly what you want. Okay, you end up with integral of this function, but this function is just h. So that shows that the result is again true when h is a simple function. Now, step 3, we are coming to the first conclusion here. Step 3, we assume that h is now measurable positive. In this case, remember that h can be written as a sequence of, like a non-decreasing sequence of simple functions. Okay? And so again, we can deduce the result for h positive measurable from that step, but also using the monotone convergence theorem. At some point, we have to exchange limit and integral once and then twice in the other direction. So we need to use the monotone convergence theorem. And that follows from the fact that the sequence of simple function can be indeed chosen to be monotone. So the proof is here. Let's assume that h is positive measurable. Then in this case, h can be written as limit when n goes to infinity of Sn. Sn are simple function like here. Okay? And we also assume that this sequence Sn is monotone, is non-decreasing. So that tells you that the expected value of h of x by this convergence is just equal to the expected value of the limit of Sn of x. Now you use the monotone convergence theorem and the fact that this sequence Sn is non-decreasing to extract the limit. Okay? Expected value of the limit is equal to the limit of the expected value. That's the same as integral of the limit is equal to the limit of the integrals because the expected value is just integral with respect to p. Alright, so we, by the monotone convergence theorem, end up here. Now, here you recognize something of the form, the same form as here, and so you can use the previous step, okay, and say that this quantity here, that's the same as here, is just equal to that, okay? So that's going to be the integral of Sn d nu x, okay? And then you again apply the monotone convergence theorem, but now not to extract the limit, but to put the limit inside the integral and say that, again, because this sequence is monotone, the limit of the integrals is equal to the integral of the limit, but the limit is just equal to h. Okay, so you again end up with expected value of h of x equals the integral of h d nu x that we have here for all h positive measurable. All right, so now last step, let's assume that h now is integrable. Okay, so remember that means that the integral of the absolute value of h, the absolute value of h d nu x is going to be finite. Okay, and in this case, we just use the fact that any function, measurable function, that can change sign, can be written as its positive part minus its negative part, but positive part and negative part are both positive measurable, and so we can use the previous step. And the fact that the integral is linear. Again, both ways, okay? So, the proof is just here. If h is now integrable, I'm going to write h as its positive part minus its negative part. So the expected value of h of x becomes expected value of h plus of x minus h minus of x. Now, because the expected value is linear, that's just equal to expected value of h plus of x minus expected value of h minus of x. Now I'm in a context where I have a positive measurable function here and there, so I can use the previous step, which tells me that those two quantities are just equal to integral of h plus d nu x, and this one integral of h minus d nu x. And then I again use the fact that the integral here is linear to be able to combine the two integrals, and you get that this is equal to the integral of h plus minus h minus d nu x, but h plus minus h minus is just x. And so that shows that indeed the change of variables formula given by this is indeed true for all positive measurable functions, but also all integrable functions. So now let's see how we can combine the notion of distribution and Radon-Nikodym derivative to define properly probability mass functions and density functions of random variables. So I remind you here the definition of a distribution, that's this new measure here that is induced by the random variable x. You have the corresponding picture here that I already explained, and I also remind you the change of variables formula that we just proved. All right, so let's assume first that x, this random variable x, is continuous. So what does it mean that x is continuous? That means that if you take any Borel set with Lebesgue measure 0, then the probability that x is in B should also be equal to 0. Okay? So what this means, again, is that if you take a Borel set B and assume that lambda B equals 0, then nu x of B, which is here, should be 0. So that's exactly the definition of absolute continuity. Okay? So if you have a continuous random variable x, then by definition of a continuous random variable, the distribution of this random variable should be absolutely continuous with respect to the Lebesgue measure. So that means that we are in the situation where we can apply the Radon-Nikodym theorem. We need one more assumption, that's sigma finiteness, but this one is easy. You just notice that, I mean, we already talked about that in the previous video. The real line with its Borel sigma algebra and the Lebesgue measure is indeed sigma finite. You can write R as a countable collection of intervals that all have finite length. Okay? So we have all the conditions to all the assumptions to apply the Radon-Nikodym theorem. Okay? So that means that eventually we get this. By the Radon-Nikodym theorem, there is some positive measurable function phi x, I'm going to call it phi x, which is the Radon-Nikodym derivative of nu x with respect to lambda. And it turns out that this is what we interpret as the probability density function of x. Okay? So, now, if you apply the change of variables formula, okay, that we just proved, And after that, you apply the Radon-Nikodym theorem that tells you that basically the integral with respect to nu x and with respect to the Lebesgue measure are related through this function. Eventually, what you obtain is the following. So you have that by the change of variable formula, the fact that expected value of h of x for any h positive or measurable is equal, or positive or integrable, sorry, is equal to the integral of h d nu x, that's the expression here. But by the Radon-Nikodym theorem, we know that we can rewrite this d nu x here as phi sub x lambda, okay? Because we have phi x is this Radon-Nikodym derivative, okay? And so eventually, we have that expected value of h of x for any positive measurable or integrable function h is going to be equal to the integral of h of x, phi of x, basically dx, if you look instead at the Riemann integral. That's a formula that we see at the undergrad level, okay? Notice that that's what we use in practice, okay, to compute the probability of an event like that involving x or the expected value of x, for instance. So if you look at this, that's the particular case where h is equal to the indicator function on the set B, on the Borel set B, and in this case, this just becomes, so here you have indicator function on B, that's the same as the integral on the set B of the density function, okay? Probability that x is in B, if x is a continuous random variable, is indeed the integral on this Borel set B of the density function, all right? Same story if you are interested in the expected value. If you look at the expected value of x, okay, you can just take h little h equals identity. That means h of little x equals little x. And in this case, you end up with expected value of capital X is equal to the integral of little x phi of x dx, or lambda dx. That's again some formula that is known at the undergrad level. All right, so eventually, to sum up, you see that if you have a continuous random variable, then its distribution is absolutely continuous with respect to the Lebesgue measure. So you can define a Radon-Nikodym derivative, and this Radon-Nikodym derivative is just interpreted as the density function of x. And you end up with this very general formula that is typically seen at the undergrad level, except that at the undergrad level, this formula for all h is extremely difficult to prove because the only tool you have is basic calculus, and so you end up with very messy algebra. At the opposite here, we have a very neat proof, very short, very elegant, more theoretical. We are using tools from measure theory, but we get a very general formula that we use in practice with a proof that is not that long, right? So notice that in the process we went from this very general probability space omega fp, and we don't really know what to do with this probability p. What is the integral of a random variable dp? That's not clear. To something a little bit nicer, which is the distribution function ux. Nicer because that's defined on the Borel sets, okay? But still, we don't really know what to do with that in practice. Now we have something that we use a lot in practice to compute the probability or expected value involving a random variable x. We only need to look at the integral of some function of x times the density function dx, or lambda dx. All right, so that was the case of continuous random variables. Now let's see what happens if you have a discrete random variable. So for instance, the example of continuous random variable that we use in practice are uniform on an interval, exponential, or Gaussian random variable, this kind of thing. Now, discrete random variable, example of such random variable would be binomial, geometric, or Poisson random variables. Right. So in this case, you see binomial, geometric, and Poisson, they all have values in the set of non-negative integers, okay? And so in this case, it's easy to see that the distribution of x, a discrete random variable with value in the set of non-negative integer, is going to be absolutely continuous with respect to something that I'm going to call the counting measure. So the counting measure just counts the number of elements in a set. Okay, so I'm calling it mu sub n, like the set of non-negative integer, and it's defined as mu n of A is just equal to the cardinal of A. That's the number of elements in A. Okay, and you do that for all A, subset of n, or you can even take subset of R, but then you have to take the intersection with n. You count the number of elements in A that are integers. Okay, so indeed, if you take a set A that does not overlap with any integer, then the probability that your random variable x belongs to A is going to be 0. Okay, so that shows that indeed your distribution function is absolutely continuous with respect to this counting measure. For all A, mu of A equals 0 implies mu x of A equals 0. So again, we are in the condition where we can use the Radon-Nikodym theorem, and then the Radon-Nikodym derivative of mu x with respect to mu n now is going to be interpreted as the probability mass function of x. Okay? So, and in this case, you can again use the change of variable formula to say that for any function h, positive, measurable, or integrable, expected value of h of x is going to be this. But because now we have this Radon-Nikodym derivative, instead of integrating with respect to mu x, that is still a very abstract measure that we don't really understand, you just have to look at the integral of h times this probability mass function, but d mu n, okay? And so eventually you obtain that. This is equal to that by the change of variables formula. But if you think about it, the integral of a function with respect to mu n is just the sum, okay? In this case, when you have a continuous random variable, you give a mass b minus a to intervals of length of this length. I mean, you give mass b minus a to the interval ab, okay? But in this case, like this measure gives a mass equal to 1 to each non-negative integer, okay? So the integral with respect to that counting measure is just equal to, well, the value of your function at those points that are in your set, okay? And so eventually that just gives you that, okay? And so you end up with expected value of h of x is just the sum of h of little x, phi of x, where in fact this quantity is the same as the probability that capital X equals little x. That's again another formula that we see at the undergrad level. You can, for instance, derive from that the formula for the expected value of a discrete random variable. If you take h equals identity, so meaning h of little x equals little x, then expected value of that, that's just the expected value of capital X, that's going to be the sum of x times the probability that capital X equals little x, okay? So again, you end up with an easy proof of expression for, in general, expected value of h of x, where h can be more or less any functions, okay? Without using any messy algebra, just using measure theory. So those things are already known again at the undergrad level, but now we have a nice proof of that, okay? So the other thing that we learn in the process is that a continuous random variable, which is characterized by a density function, a discrete random variable is characterized by its probability mass function. But you see that both the density function and the probability mass function can be viewed as Radon-Nikodym derivatives of your distribution with respect to a reference measure. And what I mean by a reference measure, it's a measure that we know better, we understand better the integral of functions with respect to those measures. And that's in this case the Lebesgue measure and the Konting measure. In the case of the Lebesgue measure, you just have a basic integral that is most of the time the same as the Riemann integral. And in the case of the Konting measure, you just end up with a sum. Okay? So, in some sense, that's the conclusion of this slide, you see that the approach of measure theory using the Radon-Nikodym theorem and the notion of Radon-Nikodym derivative, in some sense, unifies the discrete case and the continuous case. Now let's jump to another topic and look at the concept of conditional expectation of a random variable given a sigma algebra. So first I'm going to give you the general definition of that. That's a pretty abstract definition, but then after I'm going to insist on the intuition behind the definition and give you some pictures so that you can visualize this notion of conditional expectation, and hopefully that's going to give you a good intuition of what is the conditional expectation and connects your intuition of what it should be to the abstract definition. So here is the definition. So first you fix a random variable in L1 of omega fp. So omega fp is your underlying probability space. X in L1 of this space means that X is integrable, okay? And we are also going to take a sub-sigma algebra of the sigma algebra F. I'm going to call this one G. So that means that G is again a sigma algebra on omega, but that is contained in the sigma algebra F, right? So now, from that, we can define the concept of conditional expectation of this random variable X given this sub-sigma algebra G. That's by definition any random variable, so I'm using the word any, and right now we don't even know if this type of random variable exists and is unique, but we are going to prove that soon. So that's going to be any random variable Z, written like that, conditional expectation of X given G, such that, well, first thing, Z should be G measurable, okay? And in the next slides, to like shorten the notations, I'm going to just write this as Z belongs to G, okay? So what this means is that for any Borel set B, the pre-image of B by the function Z is in G, okay? And because G is a sub-sigma algebra of F, being G measurable is a stronger assumption than being F measurable, okay? So, first condition, Z is G measurable, and the second condition is that your random variable X and your conditional expectation Z should be equal on average in expected value on any sets A that is in your sub-sigma algebra G. Okay, so that's just the abstract definition. I'm going to explain the intuition behind this definition, but first let me give you two more definitions. Expected value of X given Y, where X and Y are two random variables, is defined as the expected value of X given the sigma algebra generated by Y. This sigma Y here is the sigma algebra generated by Y. That's the set of all the possible pre-images of any Borel set by this function Y. That's also the smallest sigma algebra that makes Y measurable, okay? Because now we have a sigma algebra here, we can use the previous definition to define this new object. You can also define the probability of an event given a sigma algebra. That's going to be, by definition, the conditional expectation given the same sub-sigma algebra, but of the random variable indicator function on this set B. Because this set B is an event, it's measurable, this function here, indicator function on B, is indeed measurable and so a random variable. So the definition of this object is from this one, and that's what we call the probability of B given G. All right, so we have this abstract definition. Now we know we need to kind of have an intuition of what it means. And to understand that, just think of the random variable X as a random quantity you want to study. But you don't have full information about this quantity, so it's random for you. It's not something that you know exactly, okay? And think of the sigma algebras, G and F, as the amount of information you know, okay? That's how much information you know. So you think of that, X is what you are interested in, sigma algebras are amount of information. Then, intuitively, if we have that in mind, the conditional expectation of X given G should be something like the best guess you can make about X if the information available is only G. Okay, so that's the intuition. Best possible approximation of X, but if you only know G. All right, so if you knew F, okay, because X is a random variable and so it's F measurable, then the best possible guess would be X itself, okay? You already, if you know F, then you know X, and then you know everything, and so the conditional expectation of X given F would just be X, okay? But here, you don't know F fully, you know only a subset of F, that's a partial information you know, okay? So that's the intuition behind the definition. So, why does it make sense? Well, this first part that says that the conditional expectation is G measurable means that because you only know G and not F, then you cannot have access to more than that. Okay, you only have access, based on your knowledge, to G measurable functions. You don't have access to all F measurable functions, you can only see the G measurable function. Okay, so that's this first condition says you cannot do better than that because that's only the information you know, the partial information you know. And the second condition says that that basically this random variable Z is going to be the best possible guess, like the best possible approximation, because it's equal to X on any measurable set A in G. All right, so that's kind of the definition. This is, you cannot do better than that because that's the only information you know, and then based on that, you find a function Z that satisfies that, that's the best possible approximation given the information you know. That's the intuition behind this concept, okay? So that's only an intuition and that doesn't really help to prove theorems and so on, but still that helps to have that in mind. I'm going to hopefully help you even more with more pictures that are going to give you some kind of visualization of this conditional expectation. If you know X, I mean, if you have a picture of X and a picture of G, then you can combine those two pictures to get a picture of the conditional expectation of X given G. So that's what I'm going to do now. Let's assume that your random variable X is this picture, a picture of the Mona Lisa, okay? So you can indeed think of this painting as a function, okay? In this case, omega would just be this rectangle, okay? Each little omega in capital Omega would be a point in the painting, and you can just assume that X has value in the set of real numbers, let's say for instance the interval 0, 1, okay, so uncountable set like interval 0, 1, and then each real number between 0 and 1 is going to code for a color, okay? So you can really think of this picture as a function, okay? And so that's what's going to play the role of our random variable. And so that's the object of interest. That's what you want to understand. You want to understand this picture. You want to be able to see this picture. But you don't have full information, okay? And the only piece of information you have is what's given by some sub-sigma algebra, okay? So F, the full sigma algebra F would be any Borel subset of this rectangle, okay? But then, what you only know is the sub-sigma algebra generated by all those little squares here, okay? So, the sigma algebra G corresponds to any finite union of those little squares, okay? So, now, this is your random variable, x, this is your sub-sigma algebra G. That gives you two pictures. When you combine those two pictures, you should be able to combine those two pictures to get a new picture of, but this time, of the conditional expectation of x given G. So what is this picture? How can we get this picture from the definition? Remember, the first condition is that your conditional expectation should be G measurable, okay? So in this case, because the sigma algebra G is the one generated by all those little squares, if you look at the pre-image and you call Z, like the conditional expectation, the pre-image of any Borel set by the function Z should be in this sigma algebra. So in particular, the pre-image of any singleton should be in this sigma algebra. And so from that, you can deduce that either the pre-image is empty, meaning that your function Z is not equal to this singleton anywhere, or this pre-image is going to be a union of those squares, and that means that on those squares, your function G should be constant. So the fact that Z is G measurable, where G is the sigma algebra generated by those little squares, means exactly that your random variable Z, or your measurable function Z, should be constant in each of those little squares. That's the first condition. That's what you get from the first condition in the definition of conditional expectation. The measurability condition says that if you take any of those little squares, your function Z should be constant across the square. But because we identify the value of the function with colors, that means that your new picture here should have the same color across each given square, okay? You can also say that the larger the sigma algebra, the better the resolution, okay? If I take a sigma algebra that contains more sets, then I'm going to have more precision when I look at this painting, okay? So that's the first condition. The second condition says that on any measurable set A in G, in this case that would be all the sets that can be written as a finite union of those little squares. So let's take just one square, okay? On all those sets, the expected value of Z should be equal to the expected value of X, okay? So that means that if you look at a little square here and in the original, then the common color, here you have the same color, the color you see across the square should be the average of the color from the original, okay? So, eventually you get that. The expected value condition, that's the second condition, that says that X and Z, that we are still looking for here, X and Z should be equal on average in expected value on each of those little squares. Okay, because those little squares are the ones that generate G. And then from that you deduce that the common color, we know that same color on each square from that, so the common color in each square is the average or the mixture of the colors in the same square from the original. Alright, so if you apply the two definitions, that's what you get. If your random variable is a picture like that, which is the same as the function, and your sigma algebra is something like this, then the picture here that combines both, that is the conditional expectation of x given g, should be a picture where the color in each of those little squares should be the same. And in each given square, the average of the color in each square should be the average from the original. And so eventually what you get is exactly this picture. Okay? That's just the same picture but blurry. Okay? And so that kind of shows you like some picture that illustrates the notion of conditional expectation. Okay? Here you have what you want to understand, what you want to study, but you cannot see it perfectly. You can only see it through those eyes. Okay? If you just apply the two conditions in the definition of conditional expectation, then eventually you end up with this picture. That's a visualization of the conditional expectation of x given g. Okay? So that tells you that basically that's the best possible approximation of x, okay, second condition, but using a g measurable function. In this case, that's going to be a function that is measurable for this sub-sigma algebra, and that's basically your eyes, basically. You can think of that like that. You have your original, but your vision is not perfect, and you cannot see the actual picture, you can only see an approximation of the picture. What you would see is that. Okay? Then, you see also, I'm going to add one more picture, that if you take a sub-sigma algebra of G, so something less precise than G, something that has less sets, so for instance, something like that, a sub-sigma algebra H of G. So here I chose those squares so that each square here corresponds to 4 little squares there. So indeed each finite union of squares here can be written as a finite union of those squares here. So that means that H is indeed a sub-sigma algebra of G. Then in this case, you have a smaller sigma algebra that has less sets, so you are losing some information, okay? And because you are losing some information, your precision should be less, and indeed, eventually you obtain this kind of picture, okay? Where you see even less, that's even more blurry. So now let's use again the Radon-Nikodym theorem, but this time to prove that the concept of conditional expectation we just defined indeed exists and is unique. So in this slide, I just remind you the definition of conditional expectation here, and the theorem we want to prove is the fact that the conditional expectation exists and is unique. Here, by uniqueness, we mean unique P almost surely. That means that if Z1 and Z2 are two random variables here called versions, two different versions of the conditional expectation that satisfy 1 and 2, then the set of omega in capital Omega such that Z1 of omega is different from Z2 of omega is an event that has probability measure 0. Okay? So that's what we mean by P almost surely. That's the same as the mu almost everywhere in the statement of the Radon-Nikodym theorem. We just use the word surely instead of everywhere when we deal with a probability measure. Okay, so that's the theorem we want to prove. So for that, I'm going to restrict my attention to the sub-sigma algebra G. We ignore F now. We just assume that we have our new measurable space omega G. And I'm going to assume first that this random variable x is positive. We first prove the result when this random variable x is positive, and then we can extend that to any integrable function in L1. So x is positive, and we only look at measurable sets in G. Then I'm going to define this new function here, nu of A, so nu is defined on the sub-sigma algebra, such that nu of A is equal to the expected value of x times the indicator function on the set A. Okay? expected value is the same as integral with respect to the probability measure, by definition. So you can rewrite this as the integral on omega of x indicator function on A dp, which is the same by definition as integral on the set A of x dp. Okay? So in this case, x is a positive random variable. So in particular, that's a positive measurable function. Okay? And p is a probability measure, which is a particular case of positive measure. And we saw at the very beginning of this video that if we define nu of A to be the integral on this measurable set A of a positive measure, measurable function with respect to a positive measure, then we define a new measure. We prove that this is sigma additive. Okay? So with this definition, basically what we do is we define a new positive measure. That follows from the fact that x is positive, of course. If x can be negative, then we don't have a positive measure. So we have a positive measure, and more importantly, if you take any event A in G, such that P of A is equal to 0, then this integral is equal to 0. You just look at the integral of a random variable on a set with measure 0, with probability 0. So this integral is equal to 0. So that means that nu of A is equal to 0. So in short, for all A in G, P of A equals 0 implies that nu of A equals 0. That's exactly the definition of absolute continuity. Okay? So from that, we deduce that this object here, nu, is a finite positive measure that is absolutely continuous with respect to the probability measure P. All right? This is exactly the assumption, the main assumption in the Radon-Nikodym theorem. We know that because nu is absolutely continuous with respect to P, then there exists a unique new random variable that I'm going to call Z, because that plays the role of the conditional expectation, that I'm going to call Z, and this Z is just the Radon-Nikodym derivative of nu with respect to P. Okay? So, from this we get that the Z Radon-Nikodym derivative of nu with respect to P. So we know from the Radon-Nikodym theorem that it exists, and that's unique P almost surely. Now the last question is it true that this random variable Z satisfies the two conditions, 1 and 2 here, of the definition of conditional expectation? And the answer is yes, because the measure nu is defined only on the subsigma algebra that makes this function Z G measurable, not just F measurable. That's the stronger assumption, G measurable. So we have condition 1, okay? And for condition 2, just have to remember the conclusion of the Radon-Nikodym theorem. The Radon-Nikodym theorem says that because nu is absolutely continuous with respect to P, you can define this Radon-Nikodym derivative, Z, which is the unique function P almost surely, such that nu of A is equal to the integral on the set A of Z dp. But the integral on the set A of Z dp is exactly the same quantity as that, except that X is replaced by Z, which is the same as this. So from the Radon-Nikodym theorem, we deduce that nu of A, which is that, is also equal to the same expression, but when I replace X by Z, that's exactly this condition. Okay? So we get indeed the second condition in the definition of conditional expectation. Alright, so that proves that the conditional expectation exists and is unique P almost surely for any positive random variable. Now, how can we deduce that the result is still true for an integrable random variable that might be positive and negative? We use the same trick as usual. We use the fact that any random variable, or in particular integrable random variable, can be written as its positive part minus its negative part. Positive part and negative part are two positive random variables, and then we use this step. Okay, so the proof goes like that. You just now assume that x is integrable, okay, possibly positive and negative, okay. Then I'm going to write x as x plus minus x minus, its positive part minus its negative part. By linearity of the expected value, this expected value here of x on the event A is the expected value of the positive part minus the expected value of the negative part, again on the event A. Then I can use step 1. Here we prove that there is a function z here such that this is equal to the expected value of the indicator function on A for all A in G, and this function is G measurable. I'm not going to call it z, I'm going to call it z plus instead. Same story for x minus, there exists a z minus such that z minus is G measurable, and this is equal to expected value of z minus on the event A. Okay, so that's by step 1. I can use step 1 because the positive part and the negative part are both positive measurable functions. Okay, so we get that from the previous step. And then I can again use linearity of the expected value. If I call z the random variable that is whose positive part is z plus and negative part is z minus, then that means z is equal to z plus minus z minus. And then by linearity, this is the expected value of z plus minus z minus on the event A, which is the same as the expected value of z on the event A. Okay, so that shows that, and of course, because z plus and z minus by step 1 are both G measurable, okay, the difference is again G measurable. So conclusion, for any random variable x integrable, we were able to find a function z, okay, that is G measurable, and such that expected value of x is equal to expected value of z on any measurable set in G. So that indeed proves this theorem. So now let's see how we can use this abstract concept of conditional expectation to derive formulas that I would collectively call conditioning techniques. The goal is to use this general concept to prove formulas in which you can find either like the unconditional expectation of a random variable or the unconditional probability of an event by using a conditioning. Okay, so first, I'm reminding you here the definition of conditional expectation. So, a first natural question, because z here, the conditional expectation is a random variable, a first natural question would be, what is the expected value of z? Okay, the answer is very complicated at the undergrad level. Okay, with the tool we have at the undergrad level, and that generates some very messy algebra. Especially this concept is not defined given a sigma algebra, that's defined given an event, and finding the expected value of a conditional expectation like that is quite complicated. But using this very abstract definition, it becomes in fact very easy. So, what is the expected value of the conditional expectation? That's basically what is the expected value of z. Well, you can get it from 2 here by taking a equals omega. If you take a equals omega, this indicator function becomes the function equal to 1 everywhere. Okay? And so this quantity here becomes expected value of z. And this quantity becomes expected value of x. Notice also that I can indeed choose a equals omega because omega is always in our sub-sigma algebra. That's one of the conditions of sigma algebra that should contain the full set omega. Okay? So, from the second part of the definition, we get immediately, taking a equals omega, that the expected value of the conditional expectation is just equal to the expected value of your random variable. Okay? So that's a property pretty easy to prove. So we get this. So if we write it that way, expected value of the conditional expectation is just the expected value of x, that appears to be like a property of the conditional expectation. In practice, we want to write it the other way around. We are interested in the expected value of x or the probability of an event, which is a particular case of expected value of a random variable. Okay? And to be able to compute this quantity, it helps often to use a conditioning. So to condition on something on a sub-sigma algebra, or we'll see that's going to be conditioning on a partition or conditioning on another random variable. Okay? So that's a very common technique in probability theory. So first, let's see what we get from this. If we assume that G is generated by a partition Bn, okay? So that means that you have a bunch of set Bn. The number of such set can be finite or infinite. Let's assume it's infinite for now, okay? That's, if we can prove it for infinitely many sets, that's even better, okay? And so that means that this, the elements of this sigma algebra, of this sub-sigma algebra, can all be written as a countable union of those sets, Bn. Okay. So in this case, can we use 1 and 2 to get some idea of the expression of Z? Okay. And then after, we can use this equation here and get a bunch of formulas. All right. So this context is the same as what I showed you before in this picture. Okay. Here we have sub-sigma algebra G generated by all those little squares, okay? And so now we assume that those little squares are what plays the role of those sets Bn, okay? That are the basic elements in your sub-sigma algebra. We saw, and I already explained that in details, that in each of those little squares, meaning that in each of those sets Bn, your conditional expectation Z should be constant, and the average across each square should be the same for your conditional expectation Z and your original random variable X. Okay? So from that, this picture that I explained, what we get is this, that's basically an equation that shows the previous picture. That's basically you're writing the previous pictures, but turning the previous picture into equations. Z should be constant on any of those elements, so that means that Z can be written as a sum. Let's say an infinite sum if you have infinitely many of those sets. An infinite sum of little an indicator function on Bn, okay? So Bn plays the role of the little squares on the previous picture, and an is going to be the average of colors, okay? Then, because G is generated by Bn, you can take particular sets, particular measurable sets in G, they are of the form Bn, or let's call it Bk, so that we don't have the same index. Then, if I take A here in the second condition in the definition of the form Bk here, okay, and K might be different from N. So what do I get? Well, I get that expected value of x indicator function on Bk is equal to the expected value of z indicator function on Bk. That's just this condition for a particular A. But if you go back to the definition here of z, we saw that z must be of this form. If you multiply z by indicator function on the set Bk, you end up with this sum, but where the indicator function is on the set Bn intersection Bk. Okay? Bn intersection Bk, because those sets, they form a partition, Bn intersection Bk is always equal to the empty set. Except when n equals k, in which case those two sets are both equal. They are both equal to Bn or Bk. So, in particular, z times this indicator function on the set Bk becomes just ak times the indicator function on the set Bk. Expected value of this is just going to be expected value of AK times the indicator function on BK. Bilinearly, you can put the AK outside the expected value, and the expected value of just the indicator function is the probability of the event. Okay? So eventually you end up with this is equal to AK times the probability of BK. So in this particular case, where G is generated by a partition, that's pretty easy to find an explicit expression of Z. Z is going to be the sum over n of An, but that's basically, An is basically expected value of X times indicator function on Bn divided by P of Bn. That's your average of color, okay? That's the mean of the colors, what you obtain after you mix the color on the set Bn times the indicator function on Bn. And so we get this expression eventually, okay? AK is equal to this, okay? AK is just equal to that divided by that. By definition, this expected value of X on this set BK divided by P of BK, that's also what we define at the undergrad level as the expected value of X given BK, okay? That's again, your average of color in the previous picture across the set BK, okay? So that tells you that Z eventually can be written as the sum over n, okay, of the conditional expectation of X given Bn times indicator function on the set Bn, okay? But now this conditional expectation here, it's not the same as this one. It's not the abstract definition of conditional expectation given a sigma algebra, that's just the nice conditional expectation of a random variable given an event. In this case, the event Bn. Okay? So we obtain this expression. Now we can use this and say that this expression should also be equal to the expected value of X. Okay? By this property, you see that I have to take again another expected value, but expected value of this random variable Z should be equal to the expected value of X. All right. So what can we do with that? Well, we can use this with some very, very simple algebra to get formulas that are known at the undergrad level, except that it might be tricky to prove them at the undergrad level. Again, that brings you to like some messy algebra, while here, it's just a direct consequence. You just apply basic definitions and you get it immediately. So first, let's look at the probability of an event A. Okay. So to get the probability of an event A, what I need to do here is replace X by the indicator function on this event A, and this becomes P of A. Okay? And then I can use this and that to get my result. And we get the following. So if we again condition on this partition and we take X equals indicator function on the set A, so the X here, then we get P of A equals this expected value here. That's by this property in blue, that just the expected value of the conditional expectation of the indicator function on A given G, okay? But then you go back to this other blue expression here, and if you replace X by indicator function on A, what you obtain here is expected value of indicator function on A given Bn, that's just the probability of A given Bn, that's the way the probability of an event given another event is defined. You can also see it from here. Probability of A given B is probability of A intersection B divided by P of B, okay? So you get this expression here, and then expected value, so you have an expected value of Z, so this term is not random, so you keep it, but then your expected value goes here, and expected value of indicator function on Bn, it's P of Bn. Alright, and so eventually you get that P of A is equal to the sum over n of P of A given Bn times P of Bn. That's true if the set Bn form a partition of omega. That's a well-known formula at the undergrad level. There is another way to prove it faster. It's just to use sigma additivity. You just write that P of A is P of A intersection, the union of the Bn. Because the Bn are mutually exclusive, you can put the union outside the probability and that becomes a sum. So you get P of A is equal to the infinite sum of P of A intersection Bn. But P of A intersection Bn, you see from kind of this formula, when you take X indicator function, that tells you that P of A intersection Bn is the same as P of A given Bn times P of Bn. So there is a more direct proof of that. But what's interesting here is to see that this abstract concept of conditional probability, or conditional expectation, sorry, gives you again this formula using another approach, which is a formula that we know well. Okay, so from this you can also deduce a well-known formula mostly used by statisticians, not really probabilists, that's called Bayes formula, and that tells you about the conditional probability of an element of the partition, one of the bk here, let's call it bi, given A, by definition of the conditional probability that just P of A intersection bi times divided by P of bi. But you can rewrite P of A intersection bi as P of A given bi times P of bi, and you divide by P of A, but we just prove P of A is that, so you divide by this. That's called Bayes formula. That's again mostly used by statisticians. Statisticians like to look at conditional objects. In probability, typically, we use instead this kind of formula. We are interested in unconditional objects, and you use conditioning as a tool to compute that. Okay? So, for instance, in this context, you want to use this kind of formula if the probability of Bn is not too difficult to compute, is much easier to compute than P of A itself. Okay, so let's say A is a complicated event and it's pretty difficult to find the probability of A because you don't have enough information, but let's assume that your partition Bn gives you some important information about your event A. Then in this case, that might be easier to compute P of A using this formula. Assuming that those events Bn are not too complicated, you can compute P of Bn. And assuming that, or choosing those events Bn in such a way that they give you some interesting information about A, then P of A given Bn is also easy to compute. So you end up with a sum of terms that are easy to compute, and that's how you get the probability of an event that might be complicated. All right, so now let's look at one more formula. Because I'm assuming that G is generated by a partition in this case, I can also look at the expected value of a random variable, but given another random variable, I need to assume that this other random variable is discrete. I'm going to call it y, okay? And so that's the particular case of this formula here that we proved just by taking A equals omega, so X can be whatever, but your sigma algebra, your sub-sigma algebra G, should be the sigma algebra generated by a discrete random variable Y. So what does it mean? Well, Y is discrete, so let's assume that Y takes values in the set of natural numbers, let's say, and let's call those little y. And so this sigma algebra is basically the sigma algebra generated by the events of the type capital Y equals little y. Okay? So if you use this, you are going to get, so I'm using that again, expected value of x equals expected value of the conditional expectation of x but given y, okay? Meaning given sigma of y, so that's a particular case of that. And then you can again use like this expression and say that this is also equal to the expected value of the sum here, which is the sum now, the elements of the partition that, the partition that's going to generate your sigma algebra sigma y are again of the form capital Y equals little y. So instead of a sum over n of Bn, I'm looking at a sum over y of events of the type y equals little y. So that's why this Bn becomes y equals y here. And then this indicator function is indicator function on the event y equals y, but I take the expected value. So the expected value of this indicator function becomes probability that y equals 1. That's another formula that we use also a lot. You want to understand the unconditional expected value of a random variable, but let's say it's pretty difficult because you don't have enough information to find easily the expected value, but knowing another random variable, let's call it y, then that becomes easy to find the expected value. In this case, you are in a context where assuming that your random variable y is indeed simpler than x and indeed helps you to compute the expected value of x, then this probability is not difficult to compute, and this conditional expectation also, because you know the outcome of y, the expected value given this event becomes much simpler. Okay, so this property at the opposite is quite complicated to prove at the undergrad level without using the tools of measure theory, without using this approach. And so here you have a very neat proof of this expression here. So to conclude this video, now I'm going to prove important properties of the conditional expectation itself. Okay? So in this slide, I'm reminding you again the definition of conditional expectation. So one first property that we just proved is the fact that the expected value of the conditional expectation is equal to the expected value of x. This property is important to generate what I call conditioning techniques. Those techniques are very important in probability theory. In contrast, what I'm going to do is really look at properties of the conditional expectation itself, and those properties will be important not in probability theory, but in instead stochastic processes. Why is that? Well, because the two most important types of stochastic processes are martingales and Markov chains. Martingales are defined from a conditional expectation given a sigma algebra, and Markov chains are defined from conditional probabilities given also a sigma algebra. So for those reasons, understanding the properties of the conditional expectation is important to prove that some processes, and we'll see that when I cover chapter 4 of my textbook, those properties are important to prove that some processes are indeed martingales and or Markov chains. All right, so that's the first property we proved, important in probability, not really in the context of stochastic processes. Another property that I just mentioned, but we don't use it that much, that's called the projection rule. This says that if you take two sub-sigma algebras of F, but in such a way that H is a sub-sigma algebra of G and G is a sub-sigma algebra of F, then conditioning on G and then F is the same as conditioning on H and then G, which is the same as conditioning only on H. That makes sense if you remember like the intuition behind the definition of conditional expectation. We said that some kind of best guess given the information you know. Now, if you do this double conditioning here, the amount of information you know at the end of the day is just H. So projecting, basically that's why we call that projection rule, conditioning on the two in any order is the same as conditioning on the smaller sigma algebra. One way to visualize that is just thinking really of the conditional expectation as a projection, like an orthogonal projection that would be some kind of best possible approximation, the closest point to a given point, but on a given subset. So that's just a visualization of this property, okay? Just imagine that F is your three-dimensional space. G is going to be a two-dimensional subspace of F, and H is a line, a one-dimensional subspace of G. Okay? Then, if you really think of expected value as a projection, okay, you can think of the conditional expectation of X given G as this point here. You have your random variable X, that's something that is F measurable, so that's in this space F, your three-dimensional space. But then the best possible approximation of X using an element of G, that would be this orthogonal projection here. Okay? So that's this quantity here, conditional expectation of X given G. Then given this given H, you do one more projection, but now on H, and so you end up here. Okay? Now, if you project directly on H, you kind of go here directly, and you end up with the same thing. Okay? Now, if you project on H, like here, but then you project on G, because you are already in the subspace G, you do nothing. Okay? So, those pictures, just think of that as just some kind of metaphor. Okay? But it turns out that if your random variable X is not just integrable, but square integrable, so in a space that we call L2, which means that the expected value of X squared is finite, then this topological space L2 turns out to be what we call a Hilbert space. And on a Hilbert space, you can define a notion of scalar product and projection with orthogonality and so on. And in this space L2, you can indeed visualize the conditional expectation as an orthogonal projection on the set of G measurable or H measurable functions. Okay? It's not the case if X is not in L2, but you can still have this picture in mind to have some intuition of the reason why this is true. The reason why this is true also appears in the name. It's projectional. If you project on a subspace and on another, like even smaller subspace, that's the same as projecting directly on the smaller subspace. You can think of this properly looking at those pictures also. Okay, here, remember those pictures? I have F. Basically, it's like the set of all the possible Borel subset of this rectangle. G is the subsigma algebra, the one generated by those squares. H is the subsigma algebra generated by those bigger squares. H is a subsigma algebra of G, and G is a subsigma algebra of H, so we are in the context of the previous slide. Looking at this picture through those eyes, you get that. And looking at this new picture through those eyes, you get that picture. Okay? But looking at this picture directly through those eyes, you see that again. Okay? So the result is the same. And if you look at this picture through those eyes, then even if those eyes are more precise than those ones, you have more information from this subsigma algebra than from this one. Because your picture is already blurry, you cannot make it better, and so you are not going to end up with that. You are still here. So projecting on G and H, or projecting on H and then G, or directly on H and that's it, that's the same. All right, so that's the projection rule. Then, next property, what happens when we have perfect information? Okay, I told you that you have to think of all those sigma algebras as information available. So that's the amount of information you know. Now, let's assume that X is G measurable itself. That means intuitively that if you know G, then you know X. Then in this case, what we expect is that the conditional expectation of X given G should be X itself. Okay? Because if you know G, you know X, and so you know everything about X, and so the best possible guess about X, it's X itself. Okay? And that's indeed, so that's the intuition, the result is indeed true, and that's a direct consequence of the definition. If you look at the definition of conditional expectation, you see that you need two conditions, 1 and 2. It's clear that if you take Z equals X here, this is obviously true. Okay, this is obviously true if you take x equals z. Now the problem is that x might not be g measurable. So the condition 1, which is stronger than being f measurable, might not be satisfied. But because we impose this condition, okay, you have that indeed the random variable x satisfies 1 because that's g measurable and obviously satisfies 2, okay? And so indeed when x is g measurable, the best possible guess about the conditional expectation of x given g, it's x itself. There is no approximation. We can see clearly the random variable. That's what I call the case of perfect information. Now, let's look at the opposite case, the opposite extreme, where we have no information. So what does it mean that we have no information? That means that this sigma algebra G is the smallest possible sigma algebra that is. Because a sigma algebra by definition should contain the full set omega and should be stable by complement, and so that means that this sigma algebra should also contain the empty set, then you can see obviously that the smallest possible sub-sigma algebra of F is the sigma algebra with only two sets, the empty set and the full set omega. Okay? So now let's look at this condition 1. What does it mean that a random variable is measurable with respect to this smallest sigma algebra with only empty set and omega? Well, that means that the pre-image of any Borel set by this function should be either equal to the empty set or equal to omega. And it's easy to deduce from that well, the only possibility for z is that z must be constant. Okay? So the condition 1 of G measurability, when G is like the smallest sigma algebra with only empty set and omega, tells you that Z must be constant. The conditional expectation should be constant. Okay? How do we find this constant? Well, by just looking at the second condition. So in this case, all the possible A in G are only two possible sets, empty set, omega. If I take A equals empty set, I just get 0 equals 0. That's not interesting. But if I take A equals omega, I get expected value of x equals expected value of z. Okay? So that means that in this case, where G is the smallest possible sigma algebra, that does not give any information, z must be constant, and it has expected value of x. So that means that the conditional expectation is equal to the expected value of x. That's it. Okay? That would be like, you know, if you go back to the previous picture, the only set you have is omega itself, and then the picture you see is just a rectangle with only one color, which is the average of all the colors in this painting, in the painting of the Mona Lisa. That would be kind of the analog, okay? So, perfect information means that best possible approximation is x itself. No information means that, implies that conditional expectation of x given g is equal to just the unconditional expectation of x. Now, I said no information at all, but what's important is not how much information we have, it's more how much information we have about x, okay? So, if you increase your sub-sigma algebra so that you don't have only the empty set and the full set omega, you have more sets, but this sub-sigma algebra does not give you any information about x, then in this case again, we can prove that the conditional expectation of x given g is equal to the expected value of x. So, what does it mean that g does not give you any information about x? Well, that's related in probability theory to the concept of independence, okay? Two events or random variables are independent if when you know one that doesn't tell you any, that doesn't give you any information about the other one, okay? So now we are talking about independence between a random variable and a sigma algebra that's defined this way. I'm just going to assume that y is independent of g. I'm using this notation. So now the x, I'm calling it y instead. This random variable, we assume that it's independent of the sigma algebra g. What this means is that you have independence of events as defined at the undergrad level. P of A intersection B is equal to P of A times P of B. You want this to be true for all A in the sigma algebra generated by Y. That means any set that can be written of the form Y belongs to a Borel set. And for any B in your sigma algebra G. All right. So if you have this, then we say that Y and G are independent. The random variable Y and the sigma algebra G are independent. In this case again, even if you may have some information, the information contained in G is not relevant to understand X. And so again, in this case, we expect that the conditional expectation should be equal to the unconditional expected value. Okay? So expected value of Y given G is equal to the expected value of Y. How do we prove that? The proof is here. First step, so I'm going to say that Z equals expected value of Y. That's what we want to prove. We want to prove that the conditional expectation here, Z is equal to that. So I'm just going to call Z this expected value of Y, and we need to prove that Z indeed satisfies 1 and 2. All right, so why does it satisfy 1? Well, that's clear because Z is constant equal to the expected value of Y. Okay, so if you take a constant function, the preimage of any Borel set by this function, either your Borel set does not contain the unique value of the function and so the preimage is the empty set, or your Borel set contains the unique value here, expected value of Y, and the preimage is equal to omega. Okay, so that means that any constant, okay, is always measurable with respect to any possible sigma algebra, even the sigma algebra that consists of empty set and full set. Okay, so so the fact that this constant implies automatically that we have this condition that's measurable with respect to anything. Now, to get the second properly here, I'm going to use the fact that if two random variables are independent, then the expected value of the product is equal to the product of the expected values. That's a well-known property at the undergrad level. And basically we get this. So this random variable Y and the random variable indicator function on the set A, where A is in G, those two ones are independent because A is in G and so indicator function on A is G measurable. And so those two things here by assumption are independent. Okay? So the goal to get this is to start from expected value of Y times indicator function on the set A, and we need to end up with that expected value of Z times the indicator function on the set A. How do we do this? So again, like I said, by independence we can split the expected value of the product and turn that into the product of the expected value. So that's expected value of Y times expected value of the indicator function on A. Then I can use linearity of the expected value. Okay, this is a constant. This is a constant. What's inside those quantities inside are random. They are random variables. But once you take the expected value, you just have a constant. So you can inject this constant expected value of Y inside this expected value, and you get this. But we assume Z equals expected value of Y. So that means that you can again replace that by expected value of Z times indicator function on the set A. Okay? So that indeed shows that this point number 2 is true. Okay? Here, again, the trick, what we used here that we cannot use in general, that's the fact that the expected value of the product is the product of the expected value, which follows from independence. Okay? So, now we have those two extreme cases. If X is G measurable, meaning if you know G, then you know X. In this case, the conditional expectation, best possible approximation, is X itself, no approximation at all. At the opposite, if Y and G are independent, meaning that G does not give you any relevant information about Y, then in this case, you end up with the worst possible approximation. Conditional expectation of Y given G is just expected value of Y. Now, when you have anything in between, that might be kind of tricky to really understand the conditional expectation, but often in practice, when we deal with martingales and Markov chain, you will see that processes are defined. So a process is basically a sequence of random variables that keep track of something that evolves in time, at least in the discrete time case. And very often those processes are defined as what you see in the future is equal to what you have right now plus a random increment or times a random factor. And this random increment or random factor are typically independent of the past, which means that in practice, when we deal with stochastic processes and in particular martingales and Markov chains, we'll have to deal with random variables that are basically the process in the future that can be written as the process at the current time, which is fully known, plus something that is independent of the past. And so that's something that is not known at all. So you can typically split your random variables, like break them down into a sum of something with perfect information and something for which you have no information, or as a product of those two things, okay? So now, once we have that, another natural question, and that's going to be extremely useful after, is what can we say about not expected value of any random variable given G? That would be too complicated, but expected value of a sum or a product of random variables, but in such a way that one of them is G measurable while the other one is independent of G. Okay, that's the next property we are going to look at. Sum and product, okay? You assume that X is fully known, G measurable, Y is not known at all. G does not give you any information about Y. Y and G are independent. Then in this case, the expected value of the sum given G is equal to X plus the expected value of Y. So you basically add up those two things here, okay? And the expected value of the product given G is equal to X times the expected value of Y. So you basically multiply those two quantities here, okay? So, yes, so you just do that, and so some kind of basic rule you can have in mind, even if it's not like very rigorous, what I'm saying is more or less you can deal with conditional expectation by saying that given G, everything in your expected value that is G measurable can get out, the expected value. This X gets out, this X here gets out also. While everything that is independent of G stays in the expected value without the conditioning, okay? This Y stays inside and I remove the conditioning. This Y here stays inside and I remove the conditioning. That's kind of a basic rule you can have in mind. Okay? Of course, if you have something that is neither the case of perfect information or the case of independence, that's kind of complicated. But if you can split your random variable like that into a part that is fully known and a part that is not known at all, you can kind of use this trick. Okay? So, now, how do we prove that? This one is easy, that's just a basic consequence of linearity. Okay? We know that the expected value is linear. It's easy to see that the conditional expectation given a sigma algebra is again linear, okay? And so here we can use linearity to say that expected value of x plus y given g is expected value of x given g plus expected value of y given g. But expected value of x given g by this property, that's x, and expected value of y given g by this property, that's equal to expected value of y. And so we just get that, okay? The case of the product is a little bit more tricky. So here we do the following. First, I'm going to assume that x, my random variable x here, is an indicator function. I look at just this particular case to start. Then, because x is G measurable by assumption, that means that the set B here, so that this indicator function is G measurable, this set B must be in this sub-sigma algebra G. All right, so now, if I take a set B in G, and in the definition here, I need to take a set A also in G, clearly, because G is a sigma algebra, it's stable by intersection, A intersection B is going to be in G, okay? And using this, I can write that the expected value of xy times indicator function on A is just going to be, if I replace x by indicator function on B, that's just going to be y times indicator function on A times indicator function on B, that's just the indicator function on A intersection B. Now, using the fact that A intersection B is in G, and using again this point 2 here, definition of conditional expectation, but applied to only the random variable y, that tells me that in this expected value, I can replace y by the conditional expectation of y given g. This equation here is the same as here, but in the special case where instead of x, I have y, the z here is the conditional expectation of y given g. And I can do that because now instead of an event A, I have an event A intersection B, but A intersection B is indeed in G. Okay? So we get this. Then, at this point, I can use what we proved here, because y and g are independent. The expected value of y given g is just expected value of y. So I can replace this by expected value of y. And now I can recover my random variable x here, doing like the opposite operation. This is indicator function on A times indicator function on B. Indicator function on B is just x. So eventually I end up with expected value of x times expected value of x times expected value of y times indicator function on A. So what we proved is basically point 2. For all A in G, the expected value of xy on the set A is equal to the expected value of x times expected value of y on the same set A. That shows that the conditional expectation here of xy given g is indeed equal to x times expected value of y. That shows point number 2. I skip point number 1. Point number 1 is easy. You just say that expected value of y is just a constant. So x times the expected value of y is just proportional to x, but x is G measurable. So anything that is a constant times something G measurable is again G measurable. So you can easily get that this thing not only satisfies 2 here, that's the last equation, but also you have that this part here is obviously G measurable. And so you also have condition 1. Okay, so again, now that we have those properties, I can tell you a little bit more about how we are going to use them in the context of martingales or Markov chain. In the context of stochastic processes, we are going to think of the sigma algebra as the sigma algebra generated by the process up to the present time, let's say time n. So that's what I want to call the sigma algebra of the past. That's your knowledge up from time 0 up to the present time. Okay? And typically you want to make prediction about your process, like what can we expect in the future. But typically, like I said, those stochastic processes, martingales or Markov chain, typically, like very often in practice, they are defined as sum of things that are more or less independent or product of things that are independent. So eventually you end up with expected value of something happening in the future is going to be, can be written as the state of the process at the present time, which is G measurable because you know the state of the process at the present time, but plus some random increment that is independent of the past. Okay? So that's in this context that we can use that. Same here, you just say that the value of your process in the future can typically be written, instead of a sum as a product. So that's the product of the state of your process right now that you know already, so you are in the case of perfect information, times a random factor that is typically independent of the past. And so you are again in this situation. Okay? So we are going to use those two properties in the future, in future videos, to prove that some stochastic processes, or to check that some stochastic processes are indeed martingales or Markov chain. All right. Then, one last property I will need after is the conditional expectation of a random sum. Okay, that's going to be useful to study. And I forgot something here. I should come back to that. Yeah, here I only prove the result for x equals indicator function. Okay, we need to get it for all function x that are integrable. The way we do it is by using the same technique as what I did at the beginning of this video. You can go from indicator function to simple function using the fact that simple function can be written as linear combination of indicator function and the fact that the integral is linear, or the conditional expectation here is linear. Okay, so that's how you, from this part, you can extend the result to all x simple function. Then you can go from simple function to positive measurable function. The way you do this is using monotone convergence theorem and the fact that any positive measurable function can be written as the monotone limit of a sequence of simple functions. Again, that's what we did at the beginning of this video when we looked at the change of variables formula. And then you can go from positive measurable to integrable by just thinking of each integrable function as the difference of its positive part and its negative part, and using the fact that positive part and negative part are both positive measurable function. And so you can deduce the result for integrable function from the result for positive measurable function. Okay, so that's the same pattern as what we did before. The key step is really to prove that. Okay, that's for the product. All right, so now, like I was saying, one last thing we will need after to study some stochastic processes called Galton-Watson branching processes. We need also to understand the expected value of a random sum. So what I mean by a random sum is I'm taking a bunch of random variables. I assume that those random variables are identically distributed, and instead of looking at the expected value of some of them, a fixed number of them, I'm going to look at the expected value of a random number of them. But the random number of those random variables that I take is independent of those random variables. All right, so in equation that says the following. Let's look at random sum. I assume that y1, y2, and so on, yn, and I keep going, are identically distributed, so in particular they have the same expected value. Okay? And I assume also that they are all independent of x. Okay? So I have a sequence of identically distributed random variables. They do not have to be independent, but they all need to be independent of another random variable x. I'm also assuming, so that the next thing makes sense, that x is a discrete random variable. So that's going to be defined on omega with value in the set of non-negative integer. Okay, so in this case, what I call random sum will be this sum. y1 plus y2 and so on up to yx. So I take some of those yi, but I stop at x. I take the first x of them, and x is random. That's what I mean by random sum of random variables. So in this case, we look at the expected value of this random sum, but given x. So that kind of means that you know how many terms you have here. And here, what we expect is true, is that, well, because given x, we know x. And so, same story as here, we can put x outside the conditional expectation. So, the x can get out, but then I have x of those ones, and they all have expected value, the same as expected value of y1. Okay, and they are independent of x, so indeed I have expected value of y1 and not expected value of y1 given x. Okay, so that just says that if you take a random number, or let's call it x, of those random variables, the conditional expectation of that is just like given x is just equal to x that we know times the expected value of yi in general. They all have the same expected value because they are identically distributed. So, how do we prove that? Same story as here. I don't really need to prove point 1. Okay? Clearly, expected value of y1 is a constant. Okay? And so this function is just proportional to x. And of course, by definition, x is x measurable. It's measurable for the sigma algebra sigma of x. Okay? So the fact that this random variable here is indeed g measurable, or x measurable, sorry. X measurable is obvious, okay? What's less obvious is the second point here. And to prove that, I need to look at all possible A in G, but now G is the sigma algebra generated by X. So the sigma algebra G is the one generated by the events of the type x equals little n, let's say. Okay? And because they generate G, it's enough to prove point 2 only for events of those types. Okay? And so the proof goes like that. It's enough to prove 2 for events of the type, so this A is going to be some an of the form x equals n. So set of omega in capital Omega such that x of omega is equal to n. Okay, so now I need to again look at this. So I'm looking at the expected value of the sum here, the times indicator function on this event, and I want to prove that it's the same as the expected value of this random variable on the same event. So how does it work? That's just a little calculation. Expected value of the random sum times indicator function on this event an, okay, is equal to expected value of no longer a random sum of random variables, but a fixed sum of random variables because I'm on the event an. So I know that x is equal to n. So I can replace this x here by n. I go from a random sum to a deterministic sum. It's still a sum of random variables, but I call it deterministic in the sense that we know now the number of terms in the sum. Then, next step, here you can just replace expected value of this sum because all those random variables are identically distributed. The expected value of this sum on this event, that's the same as n times the expected value of just the first one or any of them times the indicator function on an. Here, implicitly, what I'm using again is the fact that those random variables are identically distributed, okay? And so they all have the same expected value. And I'm also using kind of in the background that the expected value is linear, more or less, okay? So we get this. Expected value of n times y1 times indicator function on an. And then the last step is, again, to use this step here, okay? We can use this step because we know that y1 by assumption, or all of those yi are independent of x. So by definition of the conditional expectation, those two things should be equal. That's basically condition 2, but applied to the case where your random variable y1 here is independent of the sigma algebra. And so from this property, we can replace y1 by expected value of y1. Okay? And then I can again replace exactly like I did here. I replace x by n on this event. Now I do it the other way around. I'm saying on this event, n is equal to x. Okay? So I can replace this n by x and say that this is the expected value of x times expected value of y1 times this indicator function. This is true for all those events an. Those events generate the sigma algebra G. And so for all those events, we were able to prove that expected value of the random sum on this event is indeed equal to the expected value of this new random variable on this same event. So that indeed proves this property here. That's all for today. Thank you for watching. In the next video, I'm going to cover chapter 3 of my stochastic modeling book. That's the chapter about the convergence of random variables and limit theorems, including the strong law of large number and the central limit theorem that are two of the most popular theorems in probability theory.